This is a Lowell Observatory podcast.
5, 4, 3, 2, 1, 0.
Welcome to Star Stuff, a space oddity.
Hi, welcome to Star Stuff. I am your host, Cody Half Moon, with my brilliant co-host, Haley Osborne. And today she is going to blow our minds with the theories of the universe. What does that mean?
Okay, so this is actually going to be a two-part episode. So,
Too many theories.
I tried fitting it all into one episode, and I was like, no, we need to. So today we're mostly going to be talking about string theory and the Braneworld theory. And
The what? The brain worm theory?
Braneworld.
Ah.
I will explain.
Sounds like a Cartoon Network cartoon.
A little bit, yeah.
Okay.
So I to prepare for this episode, I actually read a book on string theory. It is called the little book of string theory. I have it in my backpack right now, actually. I thought it was a really cool book. I was really interested in it, which is weird for me because I'm weird about reading like science books or science fiction books. We've talked about this before on the podcast a couple times. But I really enjoyed that book. And then I watched like a ton of YouTube videos. I read through a bunch of stuff. And there's so much information.
Especially like
There's
I know
so much information.
like for string theory, it was really big in the early 2000s.
It was big in like the 80s.
The 80s, right.
Yeah. And then it like had a comeback.
Had a comeback. So that was when John Compton, who's been on this podcast several times, got his like master's in physics and all that.
Yeah.
And so his thing was like string theory. And then he graduated, and then people were like, okay, well, we have a new theory anyway. And he's like, well.
Yeah. So I have a lot of stuff in here. A lot of these notes, the stuff in red. So I have my outline in front of us. The stuff in red, Cody, I wrote at, I think, like 2 a.m.
It's all in red, Haley.
It's like all in red.
Okay.
And I was just like talking into my phone. So before this, you were like, should we go over the outline? And I was like, please don't look at the outline.
Maybe not. Okay.
It is just a stream of consciousness from 2 a.m., Haley. And I promise you, like, I understand what it means. But
right.
looking at it, you're going to be like, what? So,
All right. Well, let's get into it.
but yeah, let's get into it. So we're starting with string theory. I literally titled it Late Night Haley Notes. First, explain quantum. That is the first bullet point.
40 minutes later.
Literally. So I'm not gonna like fully explain it because there's just so
Well, quantum
much.
means small?
Yeah, so quantum was built to explain small and fast things. So and when I say fast, I mean like speed of light type deal. So if you were to like
V fast.
Yeah, if you were to like plot out on two axes like big versus small, fast versus slow, quantum would be in the small and fast region, and then classical mechanics would be in like the big and slow. And when I say big and slow, I mean like throwing a baseball is classical, but like atoms are like quantum, right?
Okay.
String theory lives in this realm of quantum physics, and so there's a lot to go over. So we're just gonna run into it. Okay, so the standard model is the current like universal model, right? It's called the standard model.
Okay.
It explains everything but gravity. So we tried using these things called gravitons to explain it.
Gravity, not real.
Gravity, no. No, gravity is definitely real, but the thing about gravity is it can't be explained the same way as like a lot of other things, because we talk about things in terms of like particles, right? But there aren't gravity particles, and so we tried introducing the idea of a gravity particle called a gravitron, which, now that I'm thinking about it, isn't a gravitron like a state fair ride?
It's probably. Like
I'm saying gravitron because of that. They're called gravitons, not gravitrons.
Okay.
I was like, wait, that's a
That's a
county
coaster.
fair ride. Never mind. But basically, like, it was impossible, right? And so that's why string theory was born, to try and be a theory of everything. Because, like, the big thing in physics is they are looking for some theory of everything to bridge this gap between classical mechanics and quantum mechanics. Because right now they're separate, but they both work. But they work in different ways, right? And so string theory was born to try and bridge this gap. But string theory itself has some issues.
Is it like the string between the two?
Kind of. So let me find a good thing. So I'm just going to read you this definition and then we can break it down.
Okay.
String theory, any of a number of theories in particle physics that treat elementary particles, like subatomic particles, as infinitesimal one-dimensional string-like objects rather than dimensionless points in space. Different vibrations of the strings correspond to different particles. So like one wiggles like this, that's one particle. The other one wiggles like this, that's a different particle, things like that.
Okay.
And so that's kind of like the basis of string theory, right? It was introduced in the early 1970s in attempts to describe the strong force. So there are different forces, the strong force, the weak force, the nuclear force, and another one that I don't remember. The force. The force. But it became really popular in, that was really loud. But anyway, sorry, Nate. Oh,
Nate's like, my ears.
Nate just took off his headphones. I'm so sorry. But in the 1980s, when it was shown that they might provide a fully self-consistent quantum field theory that could describe gravitation as well as the weak, strong, and electromagnetic forces. That was the other one. The development of a unified quantum theory is a major goal in theoretical particle physics, but inclusion of gravity usually leads to difficult problems with infinite quantities in the calculations. The most self-consistent string theories propose 11 dimensions, 4 corresponding to the 3 ordinary spatial dimensions and time, while the rest are curled up and not perceptible. So, thoughts?
So, 11 dimensions.
11 dimensions.
11 dimensions. 11 dimensions.
Yes.
So my brain stopped there. But I also heard four, or what was it?
4 correspond to the 3 ordinary spatial dimensions and time. So 3 spatial, 1 time. And then the theory is that the rest of them are curled up on themselves so that we don't like perceive them, because we only perceive the 4 dimensions, right? Like X, Y, Z, and time.
Everyone knows that. Yeah, of course. And so the other ones are curled up on themselves, and we do not see these dimensions. Now, are we talking like we can't see ultraviolet, or
no? We're talking like different plane of existence.
This is going to be a fun episode. Okay.
That's why I was like, this has to be 2 episodes.
Okay. So just to get it straight. So thinking of like sci-fi, which is my basis of, understanding any of this. When they talk about like, oh, we have to travel to this alternate dimension where we're an AU.
So that is different.
Okay.
And that we're actually going to talk about in the second part of this episode. Theories of the Universe Part 2.
Okay. So what's the difference here?
So what you're talking about is more multiverse. This is same universe, different dimensions within that universe.
So like we're here talking in our recording studio, and at the same time,
these dimensions
Queen of
exist
England's
around
having
us.
tea here and we don't see.
No.
Okay.
No. So like everything we know exists in those 4 dimensions. The rest of those dimensions are literally like curled up on themselves, and we do not interact with them whatsoever.
Like Interstellar with the cube?
Yeah. So like if you've seen
Spoiler
things
alert.
where there's like they call them like pan-dimensional beings or whatever, and like we can't like perceive them or whatever. That's kind of along these lines.
Like our math doesn't work, so we can't interact with it?
Not necessarily that our math doesn't work, but we just only exist in 4 dimensions, and other dimensions could be around us. And keep in mind, like all of this is very theoretical. Like string theory, it's actually not really like seriously talked about all that much anymore, because it has a lot of issues. But
Same.
yeah.
It's fine. Okay. So what would something look like in this other dimension theoretically? Or no clue. We have no idea.
Our brains don't.
So why do they think that there are a few of them?
The math works.
The math works.
So the math works so that it makes it only works if there are those 11 dimensions in certain string theory examples.
Okay.
In other string theory examples, there are 26 dimensions.
Cool. All right. 26 dimensions.
26 dimensions.
And I'm assuming we can only interact with
The four. Yeah.
Cool. This feels like they carried a number and then we're like, crap. Oh, well, we just like can't see these numbers.
Yeah, it's basically just, and this is how a lot of physics starts out, honestly. It is,
we'll deal with that later.
The math works for this case. We can prove it at another time. Because usually like the proof is way different. Like black holes were initially just mathematically this works. And then we saw one. Right? Mm-hmm. So, the thing with string theory is, string theory itself has issues, and we'll talk about a different type of string theory in a few minutes here, but basically string theory is the idea in theoretical physics that reality is made up of infinitesimal vibrating strings, smaller than atoms, electrons, or quarks. According to this theory, as the strings vibrate, twist, and fold, they produce effects in many tiny dimensions that give humans that humans interpret as everything from particle physics to large-scale phenomenon like gravity. So these tiny little strings, the idea is like, you know how matter is made up of atoms? Mm-hmm. The idea is that the atoms are made up of strings.
Okay.
Yeah. So it's like smaller and smaller, basically.
Little space worms.
Little space worms, yeah.
Okay.
Yeah. String theory in particle physics, it attempts to merge quantum mechanics with Albert Einstein's general theory of relativity, because right now they don't. Right now they don't like.
They're not friends.
They're not friends.
Okay,
they don't work. But that was like this is one of the theories that was brought up to kind of make this happen.
Okay.
So. The starting assumption of string theory is that particles are not points. Instead, they are vibrational modes of strings. No strings respond to one another in a fashion similar to gravitons. And with gravitons, the issue is you can't... I'm going to skip over that. That's a lot of just lingo.
Oh, no.
Basically, with string theory, replacing gravitons with vibrational strings smoothed out the way they interacted with one another. So gravitons... as a particle, don't work.
Right.
Gravitons as strings work better. Huh. And so this looked very promising.
Okay.
And that's one of the reasons why it got so popular.
They were getting excited.
Mm-hmm. Everybody was getting excited, right?
Okay.
So this is a lot of just, I was like literally reading the book and I was like speaking it into the document. So, now, so we get that we're talking about little strings, right?
Little baby string worms.
Little baby string worms. Now we introduce something called Dbrains, and it's Branes.
Oh, okay. Okay.
Yeah. So basically, these little strings are allowed in string theory to end in objects called Dbrains. They're basically little points that are infinitely heavy. So that the strings aren't just like, you know?
And so they all end.
They have little Dbrains on the ends.
They're all connected?
No.
No. Okay, so it's like a little dumbbell.
Yeah, think of it as like a kind of dumbbell, but it's like a string in the middle instead of bar. You know?
Okay.
That's kind of what it looked like in a lot of like the animations I watched.
Okay.
And they can be curled up in different ways depending on what type of particle they represent.
Okay.
Now, initially string theory got rid of point particles, but in the 1900s, point particles came back. And so Dbrains are point particles, basically.
Okay.
And they were introduced to make strings work. basically.
But then since they're not, people don't think that they exist now, is that kind of why string theory crumbled?
So some people still are looking into string theory. Some people think that it's got a lot of potential. So far, the type of string theory we've talked about is the least likely. There are other factors that come into something called superstring theory, which we'll go over in a sec.
Okay.
But basically, the issue with these stretch strings is the lowest energy level a stretch string has almost no vibrations. It's called the 0 point. And this is called a tachyon. Have you heard of tachyons?
I've heard of tachyons. Yes.
So tachyons are actual things in string theory. So it is imaginary because we've never seen one, and because they can't technically exist. And that was a big problem with string theory. That's one of the reasons why it kind of fell out, is because of these tachyons. If you're in that zero energy state, these tachyons basically make things bad.
So so this is the part of the string in this hypothetical string, right, where it's not vibrating.
Yeah. So they're think of them as totally separate strings, right? There's a string where it is not vibrating, 0 point. That's a tachyon.
Okay.
There's a string where it's slightly moving. That's the next particle.
I see.
On and on and on.
Okay.
But the issue with tachyons, let me see.
Why have I heard of tachyons?
Tachyons are what make the flash go fast.
Yes. Okay.
Of
course.
So if you guys are nerds like we are, the Flash, he goes really fast because of little things called tachyons, which, if string theory is real, are real.
Right.
So, yeah.
They have to be real. A tachyon has to exist for string theory to work.
This type of string theory.
This type of string theory. Okay.
But the issue with a tachyon is that because of the way it functions, and I'm not going to go super in depth into it because it was like a chapter on its own. Yeah. But the issue with tachyons is they have to have imaginary mass to work.
What does that mean? What is it?
Imaginary numbers, it'd be an imaginary mass. So think the square root of a negative. That's imaginary.
I'm going to drink my coffee.
Yeah. So have you ever seen math problems with an I in them? That means imaginary.
What does that mean though? Is that just oh, I promise, professor, this math problem works. Ignore the I. No, really, it works.
So imaginary numbers are actually used in a lot of practical applications. In the
is it you don't know what the number is, but you know a number goes there?
No. So the number technically doesn't exist, I guess. I don't know how exactly I would explain imaginary numbers, to be completely honest with you. But basically, in Hidden Figures, they are trying to figure out math that has never been invented to bring John Glenn back, right? And she goes, oh, Euler's formula. That works. And that's what they used to bring John Glenn back. Euler's formula has an imaginary number in it, intrinsically.
Cool.
Yeah. Because it's e to the I theta.
You're hey, dude, don't worry. We're getting you back. The numbers are imaginary, but it'll be fine.
So imaginary numbers are really useful in a lot of different things.
Do they function as a number? Do they?
They function as a number.
I plus 1 equals something?
Yeah, they function as a number, basically.
Okay.
Mm-hmm. Yeah.
Okay.
Yeah.
Okay.
So, but the issue here is that the tachyon would have to have an imaginary mass, which does not work. And then worse news is, so good news is that strings have vibrational modes and can act like a photon or a graviton. Perfect. Bad news is it can only do that in 26 dimensions. Worse news is that it has to have imaginary mass.
And
So this is where the theory just kind of crumbled.
Yeah.
Yeah.
An imaginary mass is there's not mass there, but pretend there is.
It's like a negative mass, basically.
A negative, a black, no, that's a lot of mass. Man?
Yeah.
Okay.
Yeah. So like this is actually one of the big things with like faster than light travel. Technically you could do faster than light travel if you had negative mass. Anyway, back to string theory.
Okay.
So people saw this issue and they were like, okay, let's fix it. So superstring theory happens.
I majored in English.
Fair. So superstring theory is born. It cures the tachyon problem and it lowers the numbers of dimensions from 26 to 10. It also produces new vibrational modes. Way more manageable. Like it doesn't sound like that much, but way more manageable. Yeah. And it also produces new vibrational modes that allow strings to act like electrons, which is important because that didn't really exist with regular string theory. And electrons are everywhere. So,
right.
Yeah. So in superstring theory, there are 9 spatial dimensions and 1 time dimension. To relate superstring theory to the world, we somehow have to do away with 6 of those 9 spatial dimensions, right? Because we have 4.
Yeah.
Or 3, not 4.
Yeah, I'd like to know about those other ones.
So,
okay.
Again, the idea is they could be curled up on themselves, things like that. But basically, the math works if there are 10 dimensions. Mm-hmm. Okay. So, the key to superstring theory is that if you start with vibrational modes or representing photons, electrons, and other particles, no matter how you collide them, you can never make a tachyon. So it definitely is better.
Mm-hmm. Mm-hmm. Well, we don't need tachyons anymore.
We don't need tachyons anymore.
We don't like tachyons.
No.
We don't like an imaginary mass. So
No,
tachyons and Flash can go in a different dimension. Okay. Mm-hmm. We like this one. It has electrons, which we know are a thing. Yep. It doesn't need tachyons, which were really confusing. Mm-hmm. We have fewer dimensions to explain away. Mm-hmm. Scientists are happier.
Yeah. Okay,
super. And that, I'm sure they're nerds. And they're like, this is super.
Yeah.
And so superstring theory.
Exactly.
Okay, it's tracking.
Now with superstring theory, we can go back to talking about Dbrains, right? That's where the string can end. And something that I found really cool that I read about was that they can actually be described as zero temperature black holes because they're infinitesimal points that are super heavy. That's what a black hole is, you know?
Yeah.
So I was reading about that and it was saying like, yeah, they could be described as zero temperature black holes. Dbrains are a particular type of brain. They're the defining property.
B-R-A-N-E.
B-R-A-N-E, yeah.
Okay.
They're a specific type of brain. They are basically defining the locations in space where strings can end.
Yes. Mm-hmm.
You get that?
Mm-hmm, mm-hmm.
Okay, cool. So, because of tachyons, usually when people are talking seriously about string theory, they talk about superstring theory, right?
Okay.
That makes sense, right?
Yes. Gone are the days of regular old string theory.
No,
we're on to
none of that.
superstring theory.
None of that. So there was a whole chapter on symmetry, and I didn't realize how ridiculous it was. But
on symmetry.
I
like symmetry.
Yeah, perfect. So the difference between string theory and superstring theory is technically symmetry.
Okay.
So when talking about symmetry mathematically, there's an argument made that a circle is more symmetrical than a square, even though they're both technically symmetrical.
Oh my God, wait. A circle is more symmetrical than a square.
Mm-hmm. Because no matter how you turn a circle, it is always symmetrical.
I love that so much.
But you can take it a step further and go from symmetry to supersymmetry by saying a sphere is more symmetrical than a circle.
That is so super. I love that. Mm-hmm. I never thought about turning the square.
Yep.
Oh my God. Yeah. These kids were definitely in the gifted and talented classes.
Crazy, right?
Wow.
Yeah. And so, like if you take a circle out of its plane of existence, you can see that it doesn't look exactly the same all around, whereas a sphere does.
That is beautiful.
So different brains, different Dbrains, have different amounts of symmetry associated with them.
Okay.
So a D0 brain has the symmetry of a sphere.
Perfect.
A D1 brain has the symmetry of a circle.
Like smooth-brained. We get it. Yeah. Okay.
And so on and so forth.
Less symmetrical. And does that affect their vibration?
Yeah, it does.
Okay.
Yeah, so different D brains will affect the
I'm so proud of
vibrations
myself right
the
now.
strings. I know. I'm so proud of you. That was good. That was really, really good.
Thank you.
Okay. So now let me look into my chaotic notes that I added on later. All right. So this is a bunch of particle physics that I am not going to explain right now.
Fermion. You know what? You're right. Let's skip over the fermion. Let's not talk about fermions. Spinors. There are so many fun words in math. Let me tell you.
We're just gonna skip
We're
over
just
that.
gonna axions.
So something that I do want to explain is this right here. So in if the 6 dimensions exist, we could be a 3D slice of a 9D universe. The 6 could be curled up on themselves like an ant on a straw. We can't get enough electrons in our particle accelerators, so we can't prove dimensions yet. So that is what that says. I know that there's a lot of, I wrote like literally just like letters for a lot of these words.
We could be a 3D slice
of a 9D universe. Mm-hmm. Which is good news.
Neither of those are your standard dice.
Well, it's good news because supersymmetry works in 10 dimensions, one of those being time, right? So technically that would be 9 spatial dimensions.
Wait, time is a dimension?
Yes. Time is a dimension.
Time is a dimension.
Mm-hmm, mm-hmm. So,
how? We're just gonna
skip that.
Oh.
Anyway,
time is a dimension.
but we could be a 3D slice of a 9D universe, which is great news because supersymmetry has 9 spatial dimensions.
I don't like all
theoretically
of these odd numbers.
Could work.
Okay.
Anyway, so crazily enough, superstring theory is actually still one of our most promising models of the universe.
Oh, no.
Oh, yeah. There's a lot we need to figure out, but good work. Good
Okay.
work. I don't know.
Okay.
And the really, really weird one is there are 5 different superstring theories. I did not look into every single one of them because I was going crazy by the end of this, but there are 5 different superstring theories. So superstring theory is the theory that you don't need tachyons anymore because we're talking about symmetry, and what affects the vibrations are how symmetrical the brains are. Pretty much, yeah.
Okay. So, and somehow this is like, hey, so we erased tachyons and now this does work, and this could be what makes up our atoms. And for this to work, because numbers apparently, there need to be 10 dimensions.
Yep.
And we can't prove that because, we can't get enough electrons?
We can't get electrons to go fast enough.
Right. So we just haven't woken them up enough to show, hey, look, there are totally other dimensions. So apparently, also, you can prove other dimensions if you can make an electron move faster. Somewhat. Yeah. Okay.
Not dimensions as in like multiverse type dimensions, but dimensions as in like spatial dimensions around us.
Like our hand going through a wall in a different...
Kinda, yeah.
Okay.
Yeah.
And there are 5 people who disagreed with each other on how this superstring theory makes sense.
There are 5 different superstring theories, yes.
Okay. So the religion turned into 5 different religions in the church. Okay. Yeah. In the Church of String, we have 5 denominations of how this works. Okay.
So yeah, that's a crash course in string theory.
Okay.
we skipped over a lot because there's a lot that we just don't have time to talk about. But if you guys are interested in it, I read the little book of string theory, and it was fascinating.
We can link it in Discord.
Yeah, I really liked it.
Okay, now is this a good place to break before we get into all of that?
So this is all for this episode.
We're good. No, we're we're in it together, guys.
We're in it together. So,
oh, my brain.
We've got one more theory that we're going to cover in this episode, and then we'll save the rest for the next episode. This next theory was the hardest theory to find information on, honestly.
Is this the Braneworld one?
Yeah.
Okay.
The Braneworld.
Braneworld, yeah.
So the Braneworld theory honestly confuses me. So I'm just going to go through it with you, and we can chat about it.
Same brain. We're talking about the brain spheres potentially at the end of each string in the string theory.
I believe so, yes.
Okay.
Mm-hmm. Okay, so the main idea here is that our three-dimensional universe is located on a brane, short for membrane. That's why it's B-R-A-N-E, membrane.
Can you say that again?
Yes. Our three-dimensional universe that we live in is located on a brane, according to this theory.
Okay.
A membrane.
Spoilers, but this is the ending of Men in Black. With the marbles. Bro, they're spheres. I think about it because it was like our universe, and it was like it showed Orion the cat. I love Men in Black. Tony Shalhoub, can we talk about it?
But
it like zooms out, and then
these brains are a little different because it's talking about them as membranes, not spheres.
Okay. So
membranes, it's like the filamental structure of the universe type deal.
Okay.
So membrane, yeah.
Yeah.
Okay. It's a multidimensional object from string theory. The brain of ours, says scientists, is inside a hyperdimensional space called the bulk or hyperspace. Interaction with extra dimensions and moving brains can have an impact on our brain with effects with effects other cosmological models don't account for.
Hyperspace. I've heard of this before.
Hyperspace,
I know. Mm-hmm. That's the space outside of space.
Yeah.
It's like Star Trek.
Yeah.
Hyperspace. To go to other places.
Pretty much.
It's like jumping out of the bubble so that you can pop back in the bubble somewhere else and be in a different place in the universe.
Yeah. But the cool thing is...
I know that one.
In 1999, physicists Lisa Randall and Raman Sundry, who I think Raman Sundry was Raman spectroscopy. Anyway, introduced a Braneworld theory that received considerable attention. Under their theory, there can be other universes just a microscopic distance away from ours, but this distance is measured in some fourth spatial dimension of which we are not aware. So that's what you were talking about with like the queen could be having tea right here.
Yes,
yeah.
and so John and I have talked about this before, and that's where he was saying like we can't exist outside of there because like when you leave our universe bubble, this is like one of the theories. I don't know if it's this one, but our physics doesn't work there.
Yeah.
So we can't be there.
Yeah.
So we
and that's
can't
what it
jump
seems
to the
like
other.
This one is all about. I'm not going to lie. Like I said, I could not find very much information on this because I don't think people are really looking into it that much anymore. But basically, the Braneworld theory predicts that relatively small black holes created in the early universe have survived to the present. These black holes with mass similar to a tiny asteroid would be part of the dark matter in the universe. And basically, these tiny black holes, that would be the brains.
For a big string.
This one's not really talking about strings.
Okay. Yeah. These are separate from the strings.
Yeah. These are two separate theories, but I believe like there's a little overlap with like the brains and everything.
Okay.
Yeah. All right.
Okay.
So
brains. Black holes.
Yeah.
Other
so
universes on a membrane.
Yeah. Here's a quote from Dr. Randall that kind of explains what you were talking about with John. Because we are imprisoned in our 3 dimensions, we can't directly detect these other universes. It's rather like a whole lot of bugs crawling around on a big 2-dimensional sheet of paper who would be unaware of another set of bugs that might be crawling around on another sheet of paper that could be only a short distance away in the third dimension.
Whoa.
Yeah.
Okay.
It's weird, right?
Yeah.
Yeah.
Is this at all connected to... No, because that's multiverse and that's a different thing. Okay. Like with the black holes, the universe, multiverse and the black holes, if they're saying that brains are...
What does this mean for our own universe? It could have itself formed from inside a black hole existing inside another universe.
Oh my God.
That was literally the next sentence on here.
Oh my God.
So the black hole episode we talked about having like different universes inside of black holes and stuff.
Us being inside one of those.
Braneworld theory would suggest we probably were formed inside of a black hole existing inside of another universe.
Well, that's fun. Okay.
All right, so I've got one last bullet point. Nate is flagging us down, doing his little dancey dance.
Yes, his little dancey dance. It's now canon.
It's now canon.
Nate dances at 45 minutes.
All right, so final bullet point. Are you ready?
Maybe.
Okay. As of now, no experimental or observational evidence of large extra dimensions as required by the Randall-Sundrum models have been reported. An analysis of results from the Large Hadron Collider in December of 2010 severely constrains the black holes produced in theories with large extra dimensions. The recent multi-messenger gravitational wave event, GW170817, has also been used to put weak limits on large extra dimensions. So basically what this is saying is because of stuff done at the LHC, Braneworld theory is probably incorrect, is what I got from this. But I could be wrong.
Right.
The thing about science is a lot of scientists have a lot of opinions on a lot of things. And so there are people who definitely are still looking into this. There are people who have completely discredited it. It really just depends on who you talk to. But as far as what I can tell from the research that I personally did setting up for this, Braneworld theory is probably not correct.
I don't want to be on a
Superstring
membrane.
theory might be correct.
Okay. Yes. I don't really want to be on a membrane of anything. That sounds gross.
Valid.
And was this the collider where everyone was like, oh my God, you're going to do bad things and the world's going to end?
Yeah.
That was fun.
Same collider.
I remember 2010.
Anyway, so that's all for this episode. If you guys really enjoyed this type of content, we are going to be posting a part 2 where we talk about multiverse theory as well as some other stuff. So definitely join in. And to all our listeners out there, please join our Discord. We've got lots of really fun stuff in there, behind the scenes content. You can also use the hashtag AskStarStuff to ask any questions you might have about life, the universe, and everything. Thanks for joining us.
Bye.
This podcast was made possible by our members and donors. If you enjoyed this episode and want to support our nonprofit in making more digital education like this available, go to lowell.edu/donate. Thanks for listening.